Now we have a whole collection of galaxies to compare to the Milky Way. Like the discovery of exoplanets only 80 years earlier, we have this whole sampling of galaxies ready made, and astronomers launch a study of these objects and comparison to the Milky Way that is still ongoing, and we're still learning a lot, as we'll see, about how galaxies work and how they form and how they interact. But we had a leftover question from the Milky Way about this crazy rotation curve. And the person who pushed the study of rotation curve was an American astronomer called Vera Rubin, who developed fantastic technology that made it very easy to measure the rotation curve of a galaxy with a single measurement, basically measuring the Doppler shift as a function of position in the galaxy, and produced large numbers of rotation curves of various spiral galaxies. And here are the kinds of results. This is actually from a paper by Rubin. And what you see is basically the same thing we saw for the Milky Way. The rotational velocity rises rapidly in the center and then oscillates a little bit and then approaches a constant. What we do not see in any of these galaxies is the decline outside the radius where the effective mass of the galaxy is. And so there's this large problem of missing mass. Is not a problem confined to the Milky Way. There is a whole component of the mass of a galaxy that we are missing. Now, once you realize this, you also realize that, like the Milky Way, many galaxies have orbiting satellites. So Andromeda has several satellites that orbit it, and other galaxies have orbital satellites that we can see. And so you can measure their orbital parameters to get a measure of the mass inside their radius, so in a larger radius. And the farther you look from a galaxy, the more the missing mass problem grows. It seems that once you get farther out, 95% of the mass of a galaxy is not accounted for by any of the components of a galaxy we have so far accounted for. So what have we accounted for? We've accounted for all the stars we can see. We might be off by some brown dwarfs. We've accounted for gas and dust that we can see. The Occam's ray and this extra matter is not clumped as tightly in the center of the galaxy. Remember, it extends, and as you go farther and farther away from the center, you're finding more and more missing mass. So this is some broadly distributed mass, a great big halo of mass around a galaxy. What's Occam's razor? Well, the first guess would be maybe there's a collection of gas. There's just a huge, we thought that maybe there were 60 billion solar masses of gas out there. Maybe there are. It turns out you need a factor of 100 more. It turns out that the visible mass of the galaxy, in the case of the Milky Way, is about 5%. We need 20 times more gas out there than we have. But if we had 20 times more gas, then we would start to see its extinction and absorption lines. We don't see any absorption lines. Whatever it is that's out there is not only not producing light, it's also not absorbing light, it's optically inactive. So we can't hide 20 times the mass of the Milky Way in gas surrounding us without being able to see it. Something that has no optical properties but is gravitationally active is an interesting thing. The name that's given to this weird stuff is dark matter. And for example, for the Milky Way, our measurements of the orbits of satellite galaxies and so on predict that there is a spherical halo. The fact that it's spherical was initially conjecture just because otherwise it would be concentrated in the disk, but later measurements of orbiting satellites and other measurements we'll discuss suggest a spherical halo. In fact, we know roughly the density profile of this dark matter halo that extends between 2 and 300 kiloparsecs, which means that if you give Andromeda a similar halo, the halo is essentially touch. And a mass, notice, that is, as I said, 20 times larger than the mass of the entire Milky Way galaxy, of all the components that we've added up so far. So most of the mass of the galaxy is in this dark matter halo. That is what the sun is orbiting. Certainly, that is, since it's a diffuse halo, the error that we found for the sun was small, but as you get farther and farther out, the differences get bigger and bigger. What is this stuff? Well, it's certainly an important thing to figure out. It dominates the galactic mass. Therefore, it is the thing that determines things like gravitational collapse and gravitational orbits and gravitational interactions between galaxies. And it's out there. What is it? Well, again, we've ruled out an envelope of gas. How else could you stick matter in a big halo around it in a way that we wouldn't see it? Well, if you clump the matter into tight clumps, like, say, brown dwarf stars, or white dwarf stars, or neutron stars, well, a neutron star packs a lot of mass into a very tight region, and so you would not see absorption lines because, by and large, you wouldn't be looking right through the neutron star. So packing matter into tight packages would be one way to hide a lot of mass in a large halo. The density of neutron stars doesn't need to be very high because there's a lot of volume there and neutron stars are very dense. So this is one suggestion. It goes under the name MACHOS for massive compact halo objects. So the search goes on. How would you find white dwarfs way out there in the halo? Well, we know that finding brown dwarfs is difficult even in the local surroundings of the thin disk, and their numbers have oscillated back and forth over the past decade. How would you find them way out there? Well, gravitational lensing is the idea. So what we see here is the light curve of a star that is not a variable star. There's no periodicity, but its brightness suddenly intensified quite significantly for a period of about 30 days and then dipped back. We have measurements here in black and a theoretical model in red that explains what it is that was going on. What was happening to this star is that it was, as the Earth moved and the Sun moved, it was for those 30 days lined up behind some dark object, like maybe a neutron star or a brown dwarf, in between us and this star. And when you have a massive object in between the star and the Earth, then what we saw is that the deflection, the gravitational deflection of light, will cause a focusing effect, so that all of the starlight that would have gone in to some angle surrounding the line, the direct line between the star and Earth, will in fact be focused by this gravitational lens, and the star will appear brighter. So this lensing effect is well understood. It's a GR effect, and I said we would apply relativity a little. So gravitational lensing, this is called microlensing because the object that's doing the lensing need not be very massive. The point is that you have to have precise alignment. And so we find these lensing events. Very good. We could use them to try to detect how often they occur. We have a sense for where stars are and assume they're scattered randomly, scatter the neutron stars in the halo randomly, and look and make predictions for the frequency with which microlensing events should occur. We do that calculation, we measure microlensing events, and we don't get nearly enough of them. In fact, no more than 10% of the missing mass of the Milky Way, say, could possibly be explained by MACHOS. And so there may be some neutron stars, though it's not clear how they got out there into the halo, but there may be some compact halo objects, but certainly that is not the answer to the missing mass puzzle. So what is it? Well, Occam's razor tells you not to add new ingredients to a theory until they're necessary, but it seems that at this point we are compelled to add a completely new ingredient to the theory. The new ingredient goes under the name WIMPs. You know that this was a naming convention by physicists when there's MACHOS and WIMPs, and the WIMPs win. WIMP stands for weakly interacting massive particles. What are these objects? Well, these are conjectured to be a completely new and yet undiscovered form of matter. We know about quarks and leptons and protons and neutrons, and there's a WIMPon, some new kind of particle that we have never detected. We have never detected it because it interacts only very weakly with matter. In fact, you can compute, just as we did for neutrinos, that hundreds of thousands of them are passing through your body at any while we're having this conversation, and because they're weakly interacting, nothing happens. Oh, wait, so why not just say there's a halo full of neutrinos? Well, neutrinos are very light objects and light particles, and they, at typical energies that you'd expect them to have, move relativistically and would not clump. Remember, these things have to gravitationally clump to be bound to the Milky Way, or bound to themselves since their mass dominates the mass of the Milky Way, into this spherical halo and not go wandering off into space. Halo made of neutrinos would not have the right properties. This is why we're talking about weakly interacting massive particles. So massive particles that interact with other particles only weakly. That's why we haven't seen them. That's why they pass through our bodies, etc. Moreover, they have to interact with each other weakly. Because if there were strong interactions, say electromagnetic interactions or electromagnetic to some other electromagnetism interactions between these WIMPs, then they would rub against each other. They would be able to lose energy and to efficiently convert gravitational potential energy into heat, and then they would collapse. We'd have black stars, and then we'd be back to the macho scenario. We want them, unlike real matter, normal matter, which has collapsed to form galaxies in which there are stars and planets and people. We want these dark matter particles to stay very smoothly distributed in this big halo and never collapse. The way they never collapse is that they don't have a way to thermalize energy. That is because they weakly interact not only with us, but also with each other. We do not know of a particle like this. So if they exist, they have not yet been discovered. And in fact, various theoretical models, ask your favorite theorist, they will have a candidate for what particle in some extension of current theories might be the candidate for dark matter. A popular candidate among many theorists is neutralinos that show up in supersymmetric extensions of the standard model of particle physics. But this is not a course on particle theory, though you might be confused sometimes. So theorists have all kinds of ideas. Experimentalists, on the other hand, want to actually detect this. Remember, 95% of the mass of the Milky Way has never been seen, is in the form of a particle we haven't discovered. Our standard model of particle physics is great for discovering the 5% we know about. Interesting and humbling. And so these are two of the many ongoing experiments. These both work on a similar principle. There are other ideas that are being conducted. The idea here is that you have these very delicate detectors. Once in a long while, one of the dark matter particles traversing the detector might interact with a proton in the detector, setting off a sound wave because it will have transferred some momentum to that proton, which will exchange it with the others in the crystal, and that sound wave gets converted to an electronic signal which will be detected. So anytime that somebody claps their hands within miles of this, the vibration is detected as a signal. And of course, lots of things might interact with a proton, so you stick these things deep in mines underground like neutrino detectors. And there are dark matter searches going on all over the world. And at some point, hopefully, we will actually have dark matter detection, and we will begin to understand the properties of whatever it is that constitutes most of the mass of our galaxy and most of the mass of the universe, as we shall see. And so, nice mystery here. We don't know what it is. There are alternatives, I should point out, to positing dark matter. They are continually being pushed into less and less reasonable corners by increasing amounts of observational data. But one of the leading ones is to say that Newtonian gravity is an approximation and that there are corrections to it, not the Einsteinian corrections that are valid at large gravitational fields and high velocities. We're talking about corrections here that would become important at large distances where the halos lie. So maybe at large distances, gravity operates a little differently, and so our Newtonian calculation of the mass enclosed was wrong. This was a reasonable theory, certainly no less reasonable than positing a whole new kind of particle, but as we'll see in a few clips, we think we have evidence to exclude that reasonable solution. There are still others in the creative minds of theorists, but most of us think that cold dark matter, as this stuff is called, is what constitutes most of the mass of the universe. One dark thing all around this halo of weird particles. We can look into the core of other galaxies, just like we tried to peer into the core of ours and see stars orbiting very rapidly. It's much easier to see the core of another galaxy if you happen to be seeing it head on. There is less of a disk of dust and gas between you and the core, and so we can extend the rotation curves all the way very close to the center, and we see that stars very close to the center, in fact, are moving at very high velocities. This tells us that very close to the center is a very massive object. Various other observations rule out most other candidates, and at the end of the day, we're led to the conclusion that, like the Milky Way, most galaxies contain in their core a supermassive black hole. In fact, the Milky Way's black hole is somewhat underwhelming. Masses of the black holes in other galaxies can be up to 1 billion solar masses, which is as much as the mass of, say, all the disk gas in the Milky Way. It turns out that the properties of the black hole in the center of a galaxy are correlated in interesting ways with galactic parameters, the luminosity of the bulge, the numbers of globular clusters. This, of course, is a great hint as to how to construct a theory of galactic evolution, where galaxies come from and how they form. We'll move to what little I'm able to confidently say about this in a bit, but for now, let's relish the fact that in the center of every galaxy is a supermassive black hole, and at the outskirts of every galaxy is this huge halo of stuff, and nobody has any idea what it's made of.